Hello friends, welcome back to my channel Chemistry Unplugged. Today we will discuss about aromaticity, aromatic compounds, antiaromatic, non-aromatic, homoaromatic and quasi-aromatic compounds. We will discuss lots of examples and previous year's problems also. So first is, what is aromaticity? Aromaticity means a compound has aromatic character or not. Aromatic systems are highly stable and we can determine aromatic systems using Huckel's rule. First is, the system should be planar or flat in nature. Second, it should be fully conjugated, means that there is proper delocalization of pi electrons. Third is, it should follow 4n plus 2 pi electron system in a closed shell. What is mean by 4n plus 2 pi electron system? For suppose there is n is equals to 0. Then according to 4n plus 2, system has 2 pi electrons, means 2 pi electron system follows 4n plus 2 rule. But these 2 pi electrons should be in closed shell. For n is equals to 1, 4 into 1 plus 2 is 6 pi electron. So 6 pi electrons also followed 4n plus 2 rule. Similarly, for n is equals to 2, it is 10 pi electron system. Then what are the anti-aromatic systems? Anti-aromatic systems are the systems which are planar in nature, means they are flat. Second, they are also fully conjugated, similar to aromatic system, but they follows 4n pi electrons in a closed shell. They have 4n pi electrons in a closed shell. First, we will discuss about 2 pi electron system. So we have 2 pi electron system should be aromatic in nature because it follows 4n plus 2 rule, but it should be cyclic in nature to be an aromatic system or in a closed shell. So we have cyclopropene in this category. It has 2 pi electrons in a closed shell. But due to the presence of this carbon, which is sp3 hybridized, there is no proper delocalization of electrons, pi electrons. So this system is not following the rule of fully conjugated system. So it is not aromatic. There is no proper conjugation because of the presence of this sp3 carbon. Hence, it is not aromatic in nature. Then, in case of cyclopropenyl cation, cation means we have to remove one H minus. Now, this carbon has plus charge, so we can write it down like this also. And because of the presence of this plus charge, this carbon is now sp2 hybridized. Means these 2 pi electron can delocalize over the system. So now it is 2 pi electron system following Huckel rule, and it is conjugation is also possible due to the presence of sp2 hybrid carbon. Therefore, this system is aromatic in nature. And because it is aromatic means it is stable. These cyclopropenyl cations are more stable than normal carbocations because of their aromatic nature. Next we take cyclopropenyl anion. Anion means this carbon has negative charge. So we have to remove H plus from the system. So after removal of H plus, this carbon has negative charge, means it has 2 additional electrons along with this pi electrons. So the system has 4 pi electrons. 4 pi electron system means this system is following 4n pi electron rule, and therefore it is anti-aromatic in nature. And because of its anti-aromatic nature, it is highly unstable. Then 4 pi electron system, we have an example of cyclopentadiene. Because it has 2 pi bonds, means it has 4 pi electrons. But due to the presence of this carbon, it has because it is a sp3 carbon. So there is no proper delocalization of electrons and the system is no longer under conjugation. So if we remove one H plus, then this will be H minus, means it has 2 electrons here. Now this system has 6 pi electrons and this carbon is sp2 hybridized. So these electrons can be delocalized over the system, and now it is an aromatic system. It is following all the Huckel rules. We can also write it down like this: negative charge is delocalized over the system. Because after the removal of this hydrogen, the system is aromatic, means if it is acid, because there is removal of one H plus from it, then its conjugated base is highly stable because it is an aromatic system. And if a conjugated base is highly stable, then this cyclopentadiene is a strong acid, and this acidity is due to these sp3 hybridized hydrogens. Now if we remove one H minus from this system, then it will become cyclopentadienyl cation, and we can also write it down like this. Now this system has 4 pi electrons, and the electrons can also be delocalized due to the presence of sp2 hybridized carbon. So it is now an anti-aromatic system, and because it is anti-aromatic system, therefore this cyclopentadienyl cation is highly unstable in nature. These charged aromatic systems are known as quasi-aromatic systems. For example, this cyclopentadiene anion is aromatic and it is also charged in nature. Therefore, these types of systems are known as quasi-aromatic systems. Then we have 6 pi electron system, and we have an example of cycloheptatriene. So it has 3 pi bonds, means 6 pi electrons. But because of the presence of this sp3 hybridized carbon, there is no proper delocalization or conjugation of electrons. So it is not an aromatic system. If we remove one H minus from this sp3 hybridized carbon, then this system becomes cycloheptatrienyl cation, or it is also known as tropylium ion. And now this carbon is sp2 hybridized and system has 6 pi electrons, therefore it is aromatic in nature. These tropylium ions are also planar in nature. It should be a planar also. Then we have cycloheptatrienyl anion, and it is 8 pi electron system because we have a negative charge on this carbon. So it has 8 pi electron system and it is planar in nature. Therefore it is anti-aromatic compound and it is highly unstable. Then we have 8 pi electron system. An example of it is cyclooctatetraene. Cyclooctatetraene has 4 pi bonds, means 8 pi electrons. So it should be anti-aromatic in nature and there is proper delocalization of electrons also, but it is not anti-aromatic because this molecule is not planar in nature. It has tub shape. So it is non-aromatic compound. Then we have cyclooctatetraene dianion, means we have 2 pair of additional electrons, and this system is now have 6 pi electrons plus 4 electrons, means it is a 10 pi electron system, and this molecule is also planar in nature. Therefore it is aromatic. Then what is we mean by non-aromatic compounds? Non-aromatic compounds do not follow Huckel rule. Okay, and second thing is that they are not planar in nature. Then what are homoaromatic compounds? Homoaromatic compounds are cyclic in nature. They have 4 n plus 2 pi electrons, but their conjugated system has at least one sp3 hybridized carbon. Okay, means their conjugation may be disrupted by sp3 hybridized carbon. Suppose we have cyclooctatetraene and we are adding acid in it. So this H plus will add to one of the double bond and we have positive charge on this carbon atom. So now it has a structure like this. So it has 6 pi electrons and this carbon is sp2 hybridized. So delocalization is possible for it, but this carbon is sp3 hybridized. So this is a proper conjugated system and has one sp3 hybridized carbon in between it. We may also write it down like this, because sp3 hybridized carbon is not in the plane, it is above the plane. So it is the proper structure of this molecule. So these types of compounds are known as homoaromatic compounds. Then what will be the stability order of these compounds? So most stable compounds are aromatic compounds, then homoaromatic compounds, then non-aromatic compounds, and antiaromatic compounds are the least stable. So aromatic compounds are most stable and antiaromatic compounds are the least stable compounds. Then heterocyclic compounds are also aromatic in nature. So first is pyridine. Pyridine is aromatic in nature and it has 3 pi bonds, means 6 pi electron system, and in addition nitrogen is also having a lone pair of electrons, but this lone pair of electron is not participating in delocalization, means they are not interacting with pi electrons. Suppose we have the structure like this and these all p electrons are in this way, they are above the plane, then the lone pair containing lobe is perpendicular to these p orbitals, means it is not interacting with other pi electrons, so it is not part of conjugation. So it has only 6 pi electron system and it is planar also, means this is aromatic in nature. Then we have pyrrole. Pyrrole has this structure and it has 4 pi electrons in the ring and 1 lone pair of electron is present on the nitrogen. And these lone pairs of electrons are present in such a way that they are interacting with pi electron clouds of pyrrole. So it is also a 6 pi electron system. If you want to write down its structure, then this will be the structure of pyrrole. The bond with hydrogen is horizontal to the p orbitals and the lone pair containing orbital is in the plane of p orbitals, so it can interact with these pi electrons. So it is a 6 pi electron system and aromatic in nature. Next we have furan. Furan has oxygen atom in a 5-membered ring and we have 4 pi electron system and 2 pairs of lone pair are present on oxygen. How they will contribute towards its aromaticity? Suppose this is the structure of furan and these p orbitals are present in this way, then one of the lone pair of oxygen is present in the plane similar to p orbitals and other lone pair of electrons are present in the plane perpendicular to the p orbital. So only one p orbital is participating in the delocalization. So it is a 6 pi electron system and it is aromatic in nature. Similarly, we have thiophene. Thiophene structure is similar to furan, but we have sulfur in place of oxygen. So its aromaticity is also similar to furan. Only one pair of lone pair is participating in delocalization while other pair is present in the plane perpendicular to the p orbitals. So it is only 6 pi electron system and it is aromatic in nature. Then we have an example of imidazole, in which we have 2 nitrogen atoms and 2 pi bonds are present in the molecule, means it has 4 pi electrons. Then this nitrogen has 1 lone pair of electrons and this nitrogen is also having a 1 lone pair of electrons. So the lone pair of this nitrogen is not participating in delocalization, or they are not interacting with the pi electron cloud of the imidazole. They are present in the plane perpendicular to the p orbitals. And this nitrogen has electrons in the plane similar to the p orbitals of carbon, so it can interact with these p orbital. So it is a 6 pi electron system, means it is aromatic in nature. Then we have aniline. Aniline means are ring compounds having conjugation. Benzene is also an aniline. It is a 6 aniline. And we have an example of 10 aniline here. So it has 10 means it has 10 carbons and it has 5 double bonds, means 10 pi electrons. So 10 pi electron system means it should be aromatic in nature. but this is not planar in nature due to the presence of these two hydrogen, repulsion between these two hydrogen, and because of its non-planar nature, the 10-aniline is not aromatic in nature. It is non-aromatic compound. And if we replace these two hydrogen with a CH2 group, then this system becomes planar in nature, and now it is aromatic because it has 10 pi electrons and it is planar also. Then it is a aromatic compound. Then we have 12 aniline and 16 aniline. 12 and 16 aniline means they are multiple of 4, means they are 4 and pi electron systems. 4 pi electron system means they may be anti-aromatic, okay? But for the anti-aromaticity, they should be planar in nature along with their conjugation. Conjugation is present, but they are not planar molecules, means they are non-aromatic in nature. Next we have 14 and 18 aniline. 14 and 18 aniline are 4 n plus 2 pi electron system. So they are aromatic because they are planar also. So they are aromatic systems. But 14 aniline has these internal hydrogens which cause steric hindrance and repulsion, and because of the presence of these hydrogens, this is less stable than 18 aniline. In 18 aniline, hydrogens are far apart from each other, so it is more stable than 14 aniline. Both are aromatic systems, but 18 aniline is more stable than 14 aniline. Then we have more examples of this. We have benzene anion, and we have to identify whether it is aromatic or not. And because of the presence of this additional lone pair of electron, we may think that this is an anti-aromatic system because it has 8 pi electrons. But these additional electrons are not in the plane similar to the p orbitals of carbon. They are in the plane perpendicular to these p orbitals. So they are not interacting with pi electron clouds. It is not a part of conjugation. So it is only a 6 pi electron system and it is still aromatic. Then we have another example of pyrrhelium ion. We have an oxygen atom in it carrying positive charge and one lone pair of electron. So it has 3 pi bonds, means 6 pi electrons, and this additional lone pair of electron is not in the plane of sp2 hybridized carbon. So it is not the part of pi electron cloud. So it has 6 pi electrons, it is a aromatic system. Then we have example of indole. Indole has 4 pi bonds, means it has 8 pi electrons, but we know that this nitrogen is also carrying a lone pair of electron. It is similar to pyrrole, and this lone pair of electron is in the plane of these p orbitals. So it is part of pi electron clouds, means it has 10 pi electrons. 10 pi electrons means it is following 4n plus 2 rule, and it is planar in nature, so it is aromatic compound. Then next question is, which is more basic? When you have such type of question, you should think that basic means it should accept one proton, and when it is accepting a proton, its conjugated acid should be stable, and if its conjugated acid is stable, means the base has more basic character. So we have to add H plus in these compounds. So first we will take this compound, and after addition of H plus, it will go on this oxygen because it has lone pair of electrons. So it will add on this oxygen. It has positive charge. Now this oxygen is carrying 2 lone pair of electrons, so it will delocalized and it will shift to this oxygen. Now you can see that this is a 6 pi electron system. 6 pi electron system means it is aromatic in nature. Aromatic in nature means it is highly stable in nature, and if conjugated acid is stable, then the base has more basic character. Now we will add one proton in dimethyl ketone or ketone acetone. Then this will also add to this oxygen and we have this structure, but it is not a aromatic system and it has not so much stability like this one, so it is less basic than this. Then write the correct order of basic nature of these compounds. We have pyridine, pyrrole and pyrrolidine. So in the pyrrolidine, nitrogen is a part of sp3 hybridized system, and we know that sp3 hybridized carbon are more basic than sp2 hybridized. So pyrrolidine is the most basic in nature. Then we have to identify which one is more basic between pyridine and pyrrole. And in the pyrrole, we know that this is aromatic due to the presence of one lone pair of electron on nitrogen, and it is part of the pi electron cloud in it. And if we add one H plus in it, then these electrons will be used and nitrogen has positive charge. So it has only 4 pi electron in it, and in the pyridine these lone pair of electrons are not the part of pi electron cloud, and if we add one proton in it, it will not lose its aromatic nature. And in the case of pyrrole, it is no more aromatic in nature after addition of proton. So when the conjugated acid is not aromatic, means it is less stable than other one. So if we number them 1, 2, 3, then pyrrolidine will be most basic, then pyridine, and least is the pyrrole because its conjugated acid is not so much stable than pyridine. Then we have other problems, and it is asked that in this triene we have to use 2 molecules of butyl lithium. Why 2 equivalents are used? Because it has 2 sp3 hybridized carbon, and these sp3 hybridized carbon are acidic in nature. Because they are acidic, because after the removal of H plus they form an aromatic system, and because it is stable, their conjugated base is stable, therefore they are acidic in nature, and now it is a part of 10 pi electron system and it is aromatic. So they need 2 equivalents of butyl lithium because of the removal of these hydrogen, so it may become a 10 pi electron system. Next is why this molecule has high dipole moment. So if we place positive charge here and negative charge here, then both system will become aromatic in nature. It is similar to tropylium ion and it is a cyclopentadienyl anion, and both systems are aromatic in nature. Because of their aromatic in nature, they are stable and they have high dipole moment. Next question is you have to identify why it is stable and this is unstable. So we can also write it down like this, and this carbon has positive charge, means it is sp2 hybridized, and now it is a 6 pi electron system with conjugation, means it is aromatic and it is stable in nature because of its aromatic nature. And in this case we have positive charge on this carbon, but this is a 4 pi electron system, means it is anti-aromatic in nature, and we know that aromatic systems are more stable than anti-aromatic system. So that's it. I will end my today's video here. Thank you so much for watching my videos. Please subscribe to my channel and press the bell icon for future notification, and please share my videos with your friends. Thank you so much.